We continue our study of which bases have primitive roots, moving on now to prime powers. So there's two theorems we're going to establish. First, if n is a power of 2, then there is a primitive root if k is 0, 1, or 2. In other words, for 2 to the 0, 1, 2 to the first 2, or 2 squared 4, there are primitive roots, but for any power of 2 higher than that, 8, 16, etc., there is not. However, if p is an odd prime, then there is a primitive root mod p to the k for any power. So the proof technique isn't only going to be different, the results are quite different. 2 to the k only has primitive roots for small values of k, 1, 2, and 4. However, p to the k for an odd prime always has a primitive root. So let's take care of our statement regarding powers of 2. For 2 to the 0, 2 to the first, and 2 squared, we claim there is a primitive root, and we're just going to find it. The order of 1 is always 1, which happens to be phi of 1 and also phi of 2. So 1 is a primitive root mod 1, but also a primitive root mod 2. Now the order mod 4 of negative 1 is 2, because the order of negative 1 is 2 for any base 3 or larger. Therefore, since 2 is equal to phi of 4, the order modulo 4 of negative 1 is phi of 4, therefore negative 1 is a primitive root mod 4. So we found a primitive root mod 1, mod 2, and mod 4. Mod 8, there isn't a primitive root. We've actually already seen this, but we can go ahead and do it again. A reduced residue system mod 8 could be, for example, 1, 3, 5, and 7. So we're going to compute the order modulo 8 of 1, of 3, of 5, and of 7. And what we end up with is, respectively, 1, 2, 2, and 2. But since phi of 8 is 4, nothing in the reduced residue system had order 4, therefore there is no primitive root modulo 8. Now we need to show that for higher powers of 2, 16, 32, 64, and so forth, there are no primitive roots either. We're going to prove the following. For any power of 2, 2 to the fourth or larger, 16, 32, etc., there is no primitive root. Now, any element of a reduced residue system modulo 2 to the k must be odd, assuming that k isn't 0, but notice we have assumed k is 4 or larger. So we are actually working modulo an even base. Therefore, any element of a reduced residue system must be odd. So let an arbitrary odd number be written as 2n plus 1. We will prove that a to the 2 to the k minus 2 is equivalent to 1 modulo 2 to the k. That will show that any odd number, and therefore any element of a reduced residue system mod 2 to the k, that the order modulo 2 to the k of a is no larger than this power. Here is a power of a equivalent to 1 modulo this base, so the order modulo that base of a can't be any bigger than 2 to the k minus 2. But phi of 2 to the k is 2 to the k minus 1, which is bigger than this. So the order of any odd number is smaller than phi of the base. Therefore, there won't be any primitive roots modulo 2 to the k. However, what we need to show is this formula right here, that a to the 2 to the k minus 2 is equivalent to 1 mod 2 to the k, where a is any odd number. So let's establish that inductively. A is equal to 2n plus 1, and what we wish to show is for any k 4 or larger, this holds. If we can show that, then we're done with working with powers of 2 and establishing which do or don't have primitive roots. So for the base case, let k equal 4. In which case, this works out to be a to the fourth. Since a was 2n plus 1, we simply expand this whole thing out and get 16n to the fourth plus 32n cubed plus 24n squared plus 8n plus 1. Okay, so do check that if you wish. However, since k is equal to 4, we're working modulo 16. Modulo 16, 16 and 32 are both equivalent to 0, and 24 is actually equivalent to 8 modulo 16. So a to the fourth is equivalent to this simpler expression. Now n is either even or odd. Now a was equal to 2n plus 1. Now n itself is either even or odd. If n is even, I'm going to write it as 2m. However, if I plug 2m in here for both of these, this produces a 32m squared and a 16m, but since I'm working modulo 16, both of these vanish and I get out a 1. So if n was even, then a to the fourth, remember a is an odd number, it's 2n plus 1. N itself, however, could be any integer. If that integer is even, a to the fourth is equivalent to 1 mod 16. But if n is odd, I can just write n as 2m plus 1, plug it in here, expand this whole thing out. This is divisible by 16, this is divisible by 16, and this is equivalent to 1 modulo 16. So whether n was even or odd, a to the fourth was equivalent to 1 modulo 16. So for any odd number a to the 2 to the 4 minus 2 is equivalent to 1 mod 2 to the 4. There's our base case. When k is equal to 4, our original claim holds true for any odd number a. We now proceed with the inductive step of this proof. We assume that any odd number a satisfies a to the 2 to the k minus 2 is equivalent to 1 modulo 2 to the k, where k is 4 or larger. We then have to show that for any odd a, we have a to the 2 to the k minus 1 is equivalent to 1 modulo 2 to the k plus 1. So assume the claim holds for all odd numbers for some particular power k. Show that it therefore holds for odd numbers for one larger power of k. We know, however, that a to the 2 to the k minus 1 is a to the, well, 2 to the k minus 1 is just 2 times 2 to the k minus 2. In other words, a to the 2 to the k minus 1 is a to the 2 to the k minus 2 squared. Okay, here, 2 to the k minus 1, I factor out a 2, but I can express this product of two things in the exponent as one exponent then raised to the other. The inductive hypothesis tells us that a to the 2 to the k minus 2 is definitely equivalent to 1 modulo 2 to the k. Therefore, I'm going to write a to the 2 to the k minus 2 as a multiple of 2 to the k plus 1. And then I just have to square that. So if I take a to the 2 to the k minus 1, we've already established it's a to the 2 to the k minus 2 squared. This is equivalent to 1 mod 2 to the k, so I replace it with a multiple of 2 to the k plus 1, and I just expand all this out. Okay, and I end up with n squared 2 to the k squared plus 2 times n times 2 to the k plus 1. Here I end up with n squared times 2 to the 2k. This 2 I can absorb into this power of 2 and call this n times 2 to the k plus 1 plus 1. Now for any k1 or larger, which certainly includes 4 or larger, 2 times k is definitely bigger than k plus 1. So this power of 2k can be written as k plus 1 plus some more stuff. It's actually a k minus 1, but whatever. So a to the 2 to the k minus 1 is n squared times 2 to the k plus 1 with more powers here, n times 2 to the k plus 1 plus 1. I can factor 2 to the k plus 1 out of both of these terms. Therefore, if I look at this modulo 2 to the k plus 1, what do I get? I get 1 modulo 2 to the k plus 1. Mod 2 to the k plus 1, this is 0, so this whole term vanishes. So having assumed that a to the 2 to the k minus 2 was equivalent to 1 modulo 2 to the k, we derive a to the 2 to the k minus 1 is definitely equivalent to 1 modulo 2 to the k plus 1. And this held for any odd number. Therefore, we've completed an inductive proof that this formula here holds for all odd numbers, and therefore all elements of reduced residue systems mod powers of 2, modulo 2 to the k where k is 4 or larger. So we've shown that modulo large powers of 2, odd numbers have orders which are just too small. Since any element of a reduced residue system mod a power of 2 has to be odd, no odd number is a primitive root mod 2 to a power, and therefore there are no primitive roots modulo 2 to powers 4 or larger. We manually showed there was no primitive root mod 8, that's 2 cubed, but there is a primitive root mod 1, 2, and 4, 2 to the 0, 2 to the first, and 2 squared. So we've completely worked out for which powers of 2 is there a primitive root, only 1, 2, and 4. Now let's turn our attention to odd primes. Okay. So now P is going to be an odd prime, and we know that odd primes always have primitive roots. So let's assume that A is a primitive root mod P. The first step in showing that all powers of P will have a primitive root is to show that either A or A plus P is a primitive root mod P squared, and therefore a primitive root modulo both. So since A is equivalent to A plus 0 mod P, in other words, it's equivalent to A plus P mod P, if A is a primitive root modulo P, then this is also a primitive root modulo P because it's equivalent. So if a was assumed to be a primitive root mod p, then so is a plus p. So both of these are primitive roots mod p. So if I can show that one of them is a primitive root modulo p squared, we will have completed the proof that there is a number that is a primitive root modulo p and also p squared. A is a primitive root mod p, so its order mod p is p minus 1. Let's denote n to be the order mod p squared of A. So I don't really know what this order is yet. I'm hoping that A might be a primitive root, but I don't know that for a fact. So I'm just going to let capital N be the order. So A to the n is definitely equivalent to 1 modulo p squared. Well, the order of any element must be a factor of the Euler-Totient function. Phi of p squared is p times p minus 1. So if n is a factor of p times p minus 1, I'm going to write p times p minus 1 is n times an integer x. In this case, a to the n, since it's equivalent to 1 modulo p squared, it's a multiple of p squared plus 1. However, if it's a multiple of p squared plus 1, while I can factor a p squared out of this, I can also factor a p. So a to the n isn't just equivalent to 1 mod p squared, it's also equivalent to 1 modulo p. And therefore, the order of a must be a factor of that power. So p minus 1 is the order of a, because it was a primitive root modulo p. So p minus 1 is a factor of n. Therefore, I'm going to write n as p minus 1 times some integer y. Now what I'm going to do is I'm going to combine this representation of n with this representation of n times x. So altogether, p times p minus 1 is nx up here, but n was p minus 1 times y. So by cutting out the middleman, I get p times p minus 1 is p minus 1 yx, and this is just equality as integers, and I can cancel out the p minus 1. This prime number p is now expressed as a product yx. But p was a prime number. How can I possibly expect a prime number as a product of two positive integers? One of them has to be 1 and the other is p. So either x is 1 and y is p, or x is p and y is 1. Since p is expressed as this factorization of x times y, that's the only factorization possible for a prime number. So here's what we have. The order mod p of a was p minus 1. We assumed a was a primitive root mod p. The order mod p squared of a, I don't know what it is, I'm calling it n. We deduced, however, that n must be able to be written as p minus 1 times y, and this integer y we deduced is either 1 or it's p. Now if y happens to be equal to p, well then, the order mod p squared of a is p minus 1 times p, but that's exactly phi of p squared, and therefore a isn't just a primitive root mod p, but it's also a primitive root mod p squared, and we're done. So let's assume that y isn't p, in which case it has to be 1. Well, if y is equal to 1, then the order mod p squared of a is n, which is now p minus 1 times 1. So the order mod p squared of a is just p minus 1. Therefore, a to the p minus 1 must be equivalent to 1 modulo p squared. Okay, so now let's let b be this other number, a plus p. Remember, the claim was that either a or this number is going to be a primitive root modulo both bases. If we're assuming that a isn't a primitive root mod p squared, hopefully b is. Okay, so b is also a primitive root modulo p because it's equivalent to a. It was just plus p. So all the same work applies as from the previous slide. The order mod p squared of b is either p minus 1 or p minus 1 times p. But we can simply compute that b to the p minus 1, well, since b is equal to a plus p, I expand this whole binomial term to the p minus 1 power according to the binomial theorem. So one thing plus another to a power, sum up over all of the possible indices from 0 to that power. The desired power here, choose the index, a to the power minus index, p to the index. So this is the binomial theorem applied to the binomial expression a plus p with a power p minus 1. Mod p squared, okay, because I'm concerned with is the order of b mod p squared something or other. So I'm going to be looking mod p squared. If I is 2 or bigger, then I'm going to have p to a power 2 or larger, and that's going to be a 0. So mod p squared, I can ignore everything except choosing I equal to 0, in which I get this, or choosing I equals to 1, in which I get this. Modulo p squared, any I past that point is going to vanish. So b to the p minus 1 is equivalent to this expression, mod p squared. It's just the first two terms of this sum. And we're now in a position to finish the proof. So we assumed that a was a primitive root mod p. Then we deduced its order mod p squared was either p minus 1 times p, in which case it is a primitive root mod p squared, or it's p minus 1 times 1. So we assumed that the order mod a of p squared was p minus 1, so it's not a primitive root mod p squared. By setting b equal to a plus p, therefore its equivalent mod p to a, so it's also a primitive root modulo p. We showed this, that b to the p minus 1 is equivalent to a to the p minus 1, plus p minus 1 times a to the p minus 2 times p, modulo p squared. However, since we did assume that the order mod p squared of a was p minus 1, a to the p minus 1 is equivalent to 1 mod p squared. And therefore, p squared is a factor of b to the p minus 1 minus all of this. And if we distribute that minus sign, we get minus 1 minus this expression here. All right, so now we know the order of p squared of b was p times p minus 1, in which case it's a primitive root and we're done, or the order mod p squared of b is also p minus 1. So assume to the contrary that b isn't a primitive root mod p squared, in which case b to the p minus 1 is going to be equivalent to 1 mod p squared. Its order was either this, in which case we were done, or this. So if we're assuming that we weren't done with the proof, the order mod p squared of b is p minus 1. So b to the p minus 1, I've raised b to its order, I get out a 1 modulo p squared. But then look back up here. So p squared must be a factor of all of this because of this line here. B to the p minus 1 was equivalent to all of this. But if b to the p minus 1 is equivalent to 1, then p squared is also a factor of b to the p minus 1 minus 1. Now, if it's a factor of one thing and the other, then it's a factor of the difference. So I'm going to take this expression here and subtract from it all of this. So p squared must be a factor of p times p minus 1 times a to the p minus 2. So I can cancel a p out of this expression and get that p must be a factor of p minus 1 times a to the p minus 2. But p is certainly relatively prime to p minus 1. Any number n is relatively prime to n minus 1. It takes a single application of the Euclidean algorithm to prove that. So since p is a factor of this product, but it's relatively prime to the first term, it must be a factor of the second. But remember that a was assumed to be relatively prime to p, which means every power of it must be relatively prime to p. Therefore, p can't be a factor of a to the p minus 2. Remember, p was an odd prime, so this power is still positive here. So, since this can't happen, we can't have this. Therefore, the order mod p squared of b couldn't have been p minus 1, so it must be p times p minus 1. And therefore, assuming a was a primitive root mod p, but not p squared, a plus p must be a primitive root modulo both p and p squared. In either case, what we have found is that there is a number that is a primitive root modulo p and is also a primitive root modulo p squared. Now that we've taken care of squares of odd primes, we can actually show that any power of an odd prime has a primitive root. So here's the final theorem we're going to prove. If p is an odd prime, there is a primitive root mod p to the k for any power of p. Well, if the power is 0, it's kind of silly, and we've already proved the claim for k equals 1 in an entirely separate video. In fact, we showed the claim for 2, and more specifically, we showed there is definitely some number which is a primitive root modulo both p and p squared. In the proof before, it was either a or a plus p. Whichever one it is, I'm just calling it a. So there is now one integer, and I'm going to call it a, and it is a primitive root modulo both p but also p squared. We're now going to show that this same integer is a primitive root for all powers of p. A is a primitive root mod p and also p squared, so the order mod p is p minus 1, but the order mod p squared is p times p minus 1. Since the order mod p squared of a was not just p minus 1, it was p times p minus 1, we know that p squared is not a factor of a to the p minus 1 minus 1. If it were, then a to the p minus 1 would be equivalent to 1 modulo p squared. But the order of a mod p squared was much bigger than just this exponent p minus 1. Now, in fact, we claim this crazy-looking formula, p to the k is not a factor of a to the p to the k minus 2 times p minus 1 minus 1 for any k larger than or equal to 2. But observe that setting k equal to 2 exactly establishes this as a base case. P squared, not a factor of a to the p to the 0 would just be 1 times p minus 1, so just p minus 1 minus 1. So our base case of k equals 2 has actually already been taken care of. Having established the base case, we should probably move on to the inductive step. So here was what we have claimed. P to the k is not a factor of all of this stuff for any k2 or larger, and we have shown that it's true for k equals 2. So let's assume the assertion holds for some value of k, 2 or larger. Now a, remember, was a primitive root modulo p. It's got to be relatively prime to p and therefore relatively prime to powers of p. Now phi of p to the k minus 1 is just p minus 1 times p to the k minus 2. So a to that power will be equivalent to 1 modulo p to the k minus 1. Therefore, if it's equivalent to 1 modulo p to the k minus 1, it's a multiple of p to the k minus 1 plus 1, or I could subtract the 1 over to this side. So either one of these two things will use each one. From the last line, we get that p to the k minus 1 is a factor of this number here, so it's also a factor of this one, because those two numbers are equal. So p to the k minus 1 is a factor of all of this. But we assumed inductively that p to the k is not a factor of all of this. Well, if p to the k minus 1 is factored out right here, but I can't factor out p to the k, then p is not a factor of n. If p were a factor of n, pop it out, get a p to the k here, but I know that p to the k can't be factored out of all this. So p cannot be factored out of n. In other words, n is relatively prime to p. Now we're going to do a bit of clever arithmetic. Take this term right here, which is from this middle line, raise it to the p power. Taking one exponent and raising it to another would just be the same as multiplying the two exponents together. P times all of this. But what is p times p to the k minus 2? It's p to the k minus 1. So this is just properties of exponents nonsense. Okay, but then what we could do is we can say this expression right here is equal to that, but this is just n times p to the k minus 1 plus 1, all raised to the pth power in here. Now, when you expand all of this to the pth power, okay, we're going to eventually reduce modulo p to the k plus 1. We're trying to prove this relationship here. We've assumed it for p to the k, and we need to now prove it for p to the k plus 1. So working modulo p to the k plus 1 is sensible enough. Now, when you expand all of this out with the binomial theorem, what you'll end up with is the sum as I goes from 0 to p of p choose I times n times p to the k minus 1 to the ith power times 1 to the p minus ith power. And of course, 1 to the p minus ith power is not really important, so we don't really need to put it there. But here is our expansion. Okay, now, if I is 3, 4, or larger, you end up with p to the 3k minus 3 or p to the 4k minus 4, etc. Okay, by taking that product there. However, all of these, 3k minus 3, 4k minus 4, and so forth, these are all bigger than k plus 1. So working modulo p to the k plus 1, all of those terms would vanish for 3 or larger, meaning the only terms we really have to worry about correspond to I equals 0, 1, or 2. Okay, so let's come back and express this, and if we are working modulo p to the k plus 1, the only powers we really need to worry about are 0, 1, or 2. So we'll come back and we'll say, while no longer equal, it is at least equivalent mod p to the k plus 1. Now, however, I want to take particular attention to the term corresponding to I equals 2. P choose 2 is going to be p times p minus 1 over 2. And then I'll have n times p to the k minus 1 squared. So here I'm going to get a p to the 2k minus 2, but I also get a factor of p from that binomial coefficient. So I actually end up with p to the 2k minus 1. And 2k minus 1 is also at least as big as k plus 1. So modulo p to the k plus 1, not only do the terms corresponding to I equals 3, 4, etc. vanish, the term corresponding to I equals 2 also vanishes. So I can, in fact, only expand this ginormous expression. I only need the first two terms as long as I am working modulo p to the k plus 1. I only need I equals 0 and I equals 1. So all of this, expand this out with the binomial theorem, and the only thing you need corresponds to I equals 0 and I equals 1. So you end up with 1 plus n times p to the k, at least modulo p to the k plus 1. But p was relatively prime to n, which means this term here is not equivalent to 0. There was no factor of p inside n, so this is not divisible by p to the k plus 1. So this is not equivalent to 0 mod p to the k plus 1, which means this thing on the left is not just equivalent to 1 modulo p to the k plus 1. In other words, p to the k plus 1 is not a factor of a to the p to the k minus 1 times p minus 1 minus 1, which is exactly the next thing we would have had to prove for our inductive argument. So inductively, we have now shown that this always holds. P to the k is never a factor of all of this for any k2 or larger under the assumption that a was a primitive root modulo p and also p squared. We're finally equipped to finish this proof. We've shown inductively that p to the k is never a factor of this expression here, provided k is 2 or larger, and a is a primitive root mod p squared. It was also a primitive root modulo p. Now we're inductively going to show that a is a primitive root for all powers of p. Our base case is already taken care of. A is a primitive root mod p squared, all the way up to p to the k, let's assume. Now let's denote the order of a modulo p to the k plus 1 as n. N has to be a factor of phi of p to the k plus 1. We're hoping it's actually equal, but at the very least it is a factor of phi of p to the k plus 1. So n is exactly the order of a mod p to the k plus 1. So p to the k plus 1 is definitely a factor of a to the capital N minus 1, because a to the capital N is equivalent to 1 mod p to the k plus 1. However, if a prime power is a factor of a number, then the prime number itself was a factor of that number. So p must be a factor of a to the n minus 1. A to the n being equivalent to 1 modulo p is exactly what's written right here. But if that holds, well then, n has to be a multiple of the order mod p of a. Since a was assumed to be a primitive root mod p, n has to be a multiple of p minus 1. So let's write it as a multiple of p minus 1. Now then, since n has to be a factor of p minus 1 times p to the k, but n is m times p minus 1, m times p minus 1 is a factor of p minus 1 times p to the k. Therefore, m must be a factor of p to the k. Well, what were the positive factors of prime powers? As we've used a few times before, p to the 0, p to the first, p squared, all the way up to p to the k are the only possible factors of p to the k. So if n is written as p minus 1 times m, then n is actually p minus 1 times some power of p, somewhere in between the 0th power and the kth power. What we're hoping for is that n is exactly phi of p to the k plus 1, because we are hoping that a is a primitive root modulo p to the k plus 1. So we want its order, which is capital N, to be phi of p to the k plus 1, p minus 1 times p to the k. We know it's p minus 1 times p to the j, so we're hoping that j equals k. Let's assume to the contrary that it's actually smaller. Okay? Well, if j is smaller than k, then j plus 1 is less than or equal to k. So k minus j plus 1 is bigger than or equal to 0. Okay, on the other hand, if I raise a to its order mod p to the k plus 1, that will be equivalent to 1. Here's the order of a, n, right? P minus 1 times p to the j. So I raise it to its order, modulo p to the k plus 1, I'm going to get out a 1. Since k minus j minus 1 is not a negative number, I can raise both sides to that power. So I'm raising both sides not to the k minus j minus 1 power, I'm raising them to the p to the k minus j minus 1 power. Since this exponent here is not negative, I don't really have a problem. So I have p to a non-negative power, I'm going to raise both sides to this power. Now if I raise this expression here to this power, I get to multiply my exponents, and I'll have p to the k minus j minus 1 times p to the j. The j's cancel, and I'll just have p to the k minus 1 times p minus 1. Now over here, I raised 1 to a power, and I can do that pretty easily. So by raising both sides to this power, p to the k minus j minus 1, I end up saying that a to the p to the k minus 1 times p minus 1 must be equivalent to 1 modulo p to the k plus 1. That, however, contradicts this formula right here for replacing k's with k plus 1s. This would tell me that p to the k plus 1 is in fact a factor of this minus 1. It's the same formula here, just shifted by one index. So therefore, j cannot be smaller than k. Therefore, j is equal to k. Therefore, the order of a is p minus 1 times p to the k. That was the order modulo p to the k plus 1, and that's phi of p to the k plus 1. So assuming that a was a primitive root modulo p squared, all the way up to p to the k, we derived it's also a primitive root modulo p to the k plus 1. And since there is always some number that is a primitive root modulo p and p squared, where p was an odd prime, we now know there is definitely a primitive root modulo p to the k, where p is any prime and k is any power. So in summary, what powers of 2 have primitive roots? 1, 2, and 4. That's it. What powers of odd primes have primitive roots? All of them.